Welcome back. Today we will discuss an interesting topic called yield line analysis of slabs. So, what is an yield line? By definition, a yield line, you know what is yield point in the case of steel, right? Similar to that, an yield line is defined as a line in the plane of a slab across the reinforcing bars have and they are yielded and about which the excessive deformation plastic rotations under the constant limit moment bracket unlimited sorry ultimate moment continues to occur leading the failure. So the explanation is not a simple explanation for a beginner. This figure will tell you clearly. Say you have a one-way slab, a continuous slab. You know that there will be a negative moment over the supports and there will be a positive moment at the mid span, right? So you know the steel in the tension side or in the mid span there will be a sagging bending moment which makes the bottom rebar to yield, so yielding of positive moment steel, and at the support region there will be a negative moment which hogging moment which results in yielding of the positive moment, sorry, negative moment steel. So this line perpendicular to this figure. So I just um, put it in pen. Okay. Suppose you have a slab like this. It's only the side view. So this line will be extended throughout the. Suppose say this is a bit the straight line is a bit direction. The yield line will be extended along the width. Okay. So these red lines are called as the possible yield lines. This is the positive yield line, and yeah, and this is the negative yield line. Yeah. So this we are going to analyze the slab for its capacity by using the yield line theory as we just introduced. So for analyzing in this way, the analysis is based on some assumptions. We can read it out. Is very important. Like the simple bending theory, also we have some assumption, which is the main part of that theory. So the yield line analysis of reinforced cement concrete slab is based on the following assumptions. One, it is that the reinforcing steel yield fully along the yield line. So along this width direction at this point, at this consecutive points along the width, the steel rebar yield equally and fully. Then B, we have the bending and twisting moments are uniformly distributed along the yield lines and have the maximum values provided by the ultimate moment capacity. So the bending moment and twisting values will be same for a single yield line. So is that the slab deforms plastically, that is the slab deformation you can see like this. It deforms plastically at failure and is separated into segments. After this failure of E line 1 and E line 2, we have this segment left. This another segment. So it is separated into segments by the E line. The individual segments of the slab behave elastically. So all the yielding happens only at this E line. The segment portion will behave elastically. And the fourth assumption is that the elastic deformations are negligible as compared with the plastic deformation. Thus, the entire deformation takes place only at the yield line, and thus the individual segments of the slabs are plane segments that collapse. So we are mainly focusing on these yield lines in a positive as well as negative moments, and we believe that these plastic regions are the main uh, contributions for the ultimate moment. Okay, next one. So next is regarding the location of E-line. So this was most or like very easy as it is spanning in a single way. We have the ultimate moment at the uh, negative moment at the supports, a positive moment at the mid span. Then for same like loading condition is like uniform. So we know that this will be the points of highest moments, either negative or positive. It was well understood. But there will be some complex situations which is shown on the right hand side, like four-way supported slab, then like a one-way slab, two-way slab, then one edge discontinuous. So these are the notations like the free, the straight line means free or unsupported edge, and like the uh, single direction hedges. It means a simply supported edge, and cross hedges we say fixed edge. So that means that for different support conditions and uh, behavior or the aspect ratio, length to breadth of the various slabs, there are chances of numerous yield lines. So we need some basic thumb rule for finding the location and the maybe the direction of the yield line. So for that, there are some inputs given. That is, in the yield line analysis of slabs, it is required to first postulate the possible yield line pattern. So by experience and by knowing the basic theory, we can find the possible yield lines locations. There may be more than one possible E-line pattern for a slab. So even for a single slab, there may be numerous possible E-line directions. So we need to analyze for all the E-line conditions, and the lowest moment which makes that yield line will be the capacity of the slab. So there may be more than one possible yield patterns for a slab. The properties of yield line assumptions made and the observed experimental phenomenon help to form guidelines for predicting the possible yield line patterns which are detailed below. So these are some guidelines. The always the yield line are straight line. So every single yield line, this is a straight line, this is a straight line, this is straight line. All the yield lines are straight lines since the intersections between the inclined planes are straight line. So all will be straight line individual yield lines. The yield line ends at a slab boundary. You can see for these type of slabs. So these these are the yield lines, and all the yield lines will either connect to another yield line, and the other side will be uh, one thing one way it is both the sides will be touching the adjacent E line, or one end to the E line and one end to supporters, which is must, or it can be either to supports. Here you can see it is to free end and this is to the simply supported edge. So the E line ends in a slab boundary. If it not so, the failure mechanism will not be complete. Okay. Then the next one is a yield line or its extension between two slab segment passes through the intersection of the axis of rotation of the adjacent two slab segments. So uh, you know that the this will be the axis of rotation of this segment. So in this figure, you have one, two, three, four segments. Here, one, two, three segments. Like, once you can count the number of segments. So all the segments will be having an axis of rotation. For this case, This will be this side. All the sides behave as the axis of rotation. The axis of rotation generally lie along the line of supports, but we just told now, and it pass over the columns if it is present. In a one-way simply supported slab, the yield line will form at the center of the slab at the bottom, and in a one-way continuous slab, which we discussed in the previous case, the yield line will occur at supports in addition to the midspan. So if it was a non-continuous beam, then the midspan moment will be the higher one, and the only yield line will be formed at the midspan. As continuous hogging moment, here also one yield line. The yield line due to sagging bending moment will be referred as the positive yield line. We already told those things. Sorry. Whereas due to hogging bending moment will be a negative yield line. The symbols for depicting the boundary conditions we just introduced are shown in figure 20.6 actually. So 20.5 is the boundary conditions and 20.6 are the various yield line for different types of slabs. And some typical yield line patterns of slabs of various shapes and boundary conditions loaded by UDL are shown in figure 20.6. So these are the possible or very commonly happening yield behavior for the various slab conditions. So, so now we understood what is an yield line, and we know that the yield line always forms at the points of highest bending moment, either negative or positive. And the yield line, how to locate the yield line, what are the conditions for that, what are the assumptions for the yield line, and these are the possible yield lines. Now we want to analyze a given slab to find the capacity of the slab. That's very important. So we learned that the capacity depends on the plastic hinge formation at the maximum moment or along the yield line, and the segment in between the yield line will behave as elastic, as in the assumption. There are basically two methods of analysis. One is actually a virtual work method, which involves some mathematical theory, and the next one is equilibrium method. Okay. These two methods should give exactly the same results because they are based on the same basic assumptions for the yield theory. So both is based on these assumptions. In either method, a yield line pattern is assumed so that the collapse mechanism is produced. The next step is to determine the exact location of yield lines. At this point, one may select either the virtual work method or the equilibrium method. So it tells that the yield line formation uh, is the base for both this theory. And after we located the possible yield lines for different slab condition, then the analysis part will be different in two methods. In the virtual work method, so according to the principle of virtual work, which means no work is done in reality, if a rigid body that is in static equilibrium under the action of a set of forces is given an virtual displacement, the sum of virtual work done by the external forces and the internal actions is equal to zero. So that means for an equilibrium state, if we given a virtual displacement, then the total work done internally will be equal to total work done externally. In this method, a work equation is used to determine the location of the yield and collapse loads. Equation is found by equating the total external work done by the collapse loads during simultaneous rigid body rotations of the slab segments while maintaining the deflection compatibility to the internal work total by the bending and twisting moments on all the yield lines. The work done can be written in the terms. So we are this is an expression that is total external work done sigma of W into delta, where delta is the virtual displacement, is equal to sigma m into theta into L, which is the internal actions. So W is the collapse load, delta is a vertical deflection through which collapse load moves, M is the moment of resistance of slab unit length, theta rotation of the slab segment to make it compatible with deflection, and L is the length of yield line. So these things will be very clear when you do a problem. So the virtual work method gives an upper bound to collapse load. So suppose the capacity of a slab is 100 in reality while you're doing the experiments, the virtual work will be always predicting a higher capacity, maybe above 100. And in the case of equilibrium method, in the equilibrium method, an equation of equilibrium is used to determine the location of the yield line and the collapse load. And the equations are formed by equating the external load to the internal forces while maintaining the deflection compatibilities ensured in both the cases. Thus, the equilibrium method gives a lower bound to the true collapse load. So, if it was exact value is 100, then this will predict some 80, which is always safe, or which is good, taking considering the factor of safety. The equilibrium condition is set in such a way that the mathematical differentiation is avoided as in the virtual work method. So in the following sections, we will just see what is the difference between the virtual work and the equilibrium method. So that will be illustrated by an analysis on one-way slab and the two-way slab. Yeah. So we will first see the analysis of one-way slab. So this is a one-way slab, which is a continuous slab. So let's consider a 1 meter wide strip. So this is the length direction. Consider a 1 meter wide slab strip, continuous one-way slab shown in figure 20.7 and 20.7b. It is shown here. Let M0 be the ultimate moment of resistance per unit length for midspan at the positive border reinforcement. So for these conditions, being a continuous beam, assume that the maximum moment happens at this point. Okay, because it depends on the as it's continuous, it need not be at the center point. It depends on the loading and the other connection, like the support conditions. So M0 is the ultimate moment of resistance per unit length for midspan for the positive border reinforcement, and Mij and Mj. Mi is here, sorry, Mi is here, and Mj is here. They are the ultimate moment of resistance per unit length for the negative reinforcement. It supports I and J. So this is support I, support J. These are the Mi and Nj are the negative moments. And W is the collapse load per unit length of slab. This is the collapse. UDL is given W. L is the span between the I and J supports. Theta I and theta J are the angles. You can see here. Theta I is the angle from the I support, and theta J is from the J support. So when you first you let's see this figure in a clear way. We know I support, J support. The Mi is the internal moment at supports, Mj internal moment at support J, and W is the collapse load length section of slab. So we know at the supports we have the negative yield line for this 1 meter slip. 1 meter is here. So this is the top view, okay. And the assume that we are uh, getting a positive moment here. This is the yield line, positive yield line, and negative yield line always at supports 1 meter strip, and showing the location of yield line. And so these things which acts as the base for both the virtual work method and the equilibrium method. So this is for the virtual work method. So we just took the important things, parameters Mi, W collapse load, Mj. So it will collapse like this. Just a minute. Yeah, okay. So we are assuming that the slab collapse in like this way, making this as the yielding of reinforcements happens at this point, this rounded point. Yeah. So here, so take the this angle as theta I, and this angle theta j, and we this deflection, vertical deflection is actually a delta, and as this is theta I, this will be also theta I, this theta j, this also theta j. So these are the solutions we need for solving in virtual work method. And parallelly see this one, the equilibrium method, same thing. We have the reaction Ri, reaction Rj, which comes in addition to the previous figure, reactions Ri, Rj. And other things, Mi is fine, Mj is fine. The support moments, internal moments. M0 is the positive bending moment, internal. Then W is collapse load. So yeah, so these things are clear to you. So I have just placed that figure for your understanding at this right top point. Okay, now we will try to analyze it. So the left side, it shows the analysis of slab. Excuse me, I'll take a water. Yeah. So the analysis of slab will be done in two methods: the virtual work method and the equilibrium method. First one is the virtual work method, and second one is the equilibrium method. So we know by virtual work method, what was the definition? That is, for rigid body in static equilibrium under the action of set of forces, and for a given virtual displacement, the sum of the virtual work done by external forces and the internal actions is equal to zero. That is, total external work done is equal to internal work. Okay, so that thing. So external work done, EWD, is equal to W into X. So this X is the newly introduced term. So we don't know exactly at what point the maximum bending moment, positive bending moment will happen. So we take this distance as X. Okay. So W into X will be the total load. W into X into delta by 2. Why delta by 2 means? We know that uh, the vertical deformation at this point is a combination of the left hand side as well as the right hand side. So treating equal displacement offered by both left and right, the for the left, W into X total load delta by 2 plus W into total length is L. So L minus X will be the remaining length into delta by 2 will be equal to WL into delta by 2 will be the total external work done. Internal work done is equal to M theta. So moment into theta will Mi into theta I plus, how to find this one? This is actually, uh, yeah, you can take this moment, uh, just a minute. I think now that figure is clear. So Mi into theta I. So this moment into this theta I will be the total work done at the left hogging portion plus M0 is a positive bending moment. So M0 into total deformation is theta I plus theta j is total deformation, plus Mj right side into theta j will be the total internal work done. So from the figure we can find theta I is equal to delta by x. So theta I is equal to delta is full depth by x is here will be theta I, and theta j will be delta by L minus x. Substituting the value of theta I in the equation of IWD, we will get Mi into delta by x plus M0 into uh, this equation uh, for theta I and theta j plus mj into theta j we have expressed like this. Then we know that in the virtual work method, total external work done is equal to total internal work done. So we are equating W into L by 2, sorry, W into L into delta by 2 is equal to the right hand side. We will get W from this equation as 2mi by Lx is equal to 2m0 by x into L minus x plus 2mj by L into L minus x. So this will be the expression obtained, and we need to find the minimum value of the collapse load, because we are going to design, or the lowest value will be the prominent one. So here involves the mathematical part, which we told required for virtual work method. We want to differentiate the load with respect to x to solve the equation and find the equations for the lowest W value. So we'll get mj minus mi into a square. So this equation will uh, give you the lowest capacity or lowest collapse load for the one-way slab continuous by Birchbach method. Okay, so we will see one more method, the equilibrium method. So by the equilibrium method, uh, it was told in equilibrium method an equation of equilibrium is used to determine the location of yield line and collapse load. So we will come back to our basic equilibriums, static equilibrium for analysis used in the mechanics, engineering mechanics. There is sigma v is equal to 0, sigma m equal to 0 equation. So that's why we introduced the reactions Ri, Rj here. Yeah. So in the equilibrium method, the plastic hinge will occur at the section of maximum bending moment, and shear force will be zero at the section. So we always know at the points of maximum bending moment, the shear force will be zero. And this condition may be used to determine the two unknowns x and w. So x is the length at which the maximum bending moment happens, and w is the collapse load required. So we have the value Ri is equal to W into L by 2 plus Mi minus Mj by L. So this will give you the reaction at Ri. Yeah, the figure is here. So this so Ri, Rj. Uh, just if you ignore the moments, total load W into L by 2 equally to left and right supports plus difference between Mi minus Mj all divided by L will give you the support reaction Ri. Similarly, for Rj also you can find the difference happens only in this sign. Yeah. So the two equations of equilibrium, as we told, sigma b 0, sigma m 0. So the Ri minus Wx is equal to 0. So we are considering this part where the possible failure in positive moment happens. So Ri minus W is equal to 0, first equation. Or for the right hand side, W L by 2 plus Mi minus Mj by L is equal to L minus W is equal to 0. Okay, so this is obtained by using this equation Ri. Then from this equation, W is equal to 2 into Mj minus Mi by L into L minus 2x. Again, okay, this so this equation of W is from the sigma v equal to 0 equilibrium. And next is regarding the bending moment equation. So Ri into x is the bending moment minus mi minus wx square by 2 minus m0 equal to 0. So all the moments m0, mi, wx square by wx square by 2 is the moment due to this UDL. Ri into x is the bending moment due to support. So sigma m equal to 0 is used here. Sorry, 0 is used here. And by solving this equation we will get the uh, solving this equation and put the value of w, we will get the equations similar as we got for the virtual work method. So like mj minus mi into s square plus 2 into mi plus m0 into lx minus mi plus m0 and l square is equal to 0. So you can see that the total calculations got almost half in the case of equilibrium method, and hereafter the equilibrium method will be the most preferred one, and it is not mathematically difficult to solve for the collapse load. So this is the general equation, and so this is general equation, and the solution for W and X depends on the slab conditions, as I told, like the behavior of the slab, support conditions, all such things will be dependent. So in the case of simply supported slab, simply supported means you know that the both the hogging moments will be zero. So Mi Mj will be zero, and the value of W and S can be obtained from equations from the previous equation. So that means that this Mi and Mj will be 0. That will give, yeah, so from the equations, just a minute. Yeah, from the equations of W, we can find that the moment in the case of simply supported beam, the Mi and Mj will be equal to 0. Substituting the values, we will get the solution of x as L by 2, like the normal beam, which normal beam means simple supported beam UDL. We have the positive bending moment at the mid span. X is WL L by 2, and W is equal to 2 M0 by X into L minus X is equal to 8 M0 by L square. So this equation is quite familiar to you. That is, when the L square goes to left hand side, M0 is equal to W L square by 8, which is the bending moment. So by rearranging, like M is equal to W into L square by 8. Very familiar equation to you, right? You will get 4 simply supported for the fixed ends. Mi will be equal to mj, and you can use the equation 20.2 and 20.3, 20.2 and 20.3 to solve for the w will be w is equal to 24 into m0 by l square. So a simple problem, uh, the last problem for today, and the factored moment capacities of a one-way continuous slab are Mi 12, Mj 10, 20, and M0 16. If the span of the slab is 4.8 meter, determine the location of the plastic hinge and the collapse load. So it's given one-way continuous from equation 20.3, which we have derived the last equation for both the methods. We have the mj minus mi into square plus 2 into mi plus m0 into or into lx minus mi plus m0 into l square 0. So putting the values and solving, that means we can apply these values of 12. So this is actually zero. That means we know the length, we know the mi, m0, all things is known to you. We can find for the x. It's clearly the direct way. X is 2.25. So substituting the value. So see that yeah, the reason why we didn't get exactly at the middle is that the mi and mgrs are different moments. Mi and Mj are different moments. That makes the beam to collapse for the positive moment at a location different from the midspan. Suppose this Mi and Mj was equal, then the positive moment will be happening at the exact midpoint. So due to this changed values, the x become out of 4.8 meter. The in real not reality. Normally it should come 2.4 exactly at the center, but we got at 2.25 meter towards the left side, as we had a higher moment at the j side, right? Because x is measured from the left. So these are the shear force pattern. 28.23 higher moment at MJ will give more reaction support, less for left side, and even the moment also high for right side, left 12, and midspan moment is 12. So for these conditions, we got x is equal to 2.25 will be the location of the E line, and at this point there will be E line like this, which is perpendicular to this uh, beam direction. So now we know how to. So this will be the common equation for all the case of one-way slab, and you can apply the values known to you, and the condition is what, like we just put for simply supported slab and the fixed end beam to solve for the collapse load as well as the location of the E line. Right. So that's the end of today's presentation. Thank you.